Welcome back. We're going to pick up now on physical memory. Actually, just out of curiosity, anybody here that wasn't in part 1? All right, you need to leave, sir? I'm just kidding. In this section, we're going to focus entirely on physical memory, and I just, again, want to reinforce one more time, as I said at the beginning of the talk, that the connection between virtual and physical is what you just saw in terms of impact on the system of virtual memory in terms of physical memory. And that connection was the system commit limit and the fact that the system commit limit is related to the amount of RAM you've got. Now we're going to focus completely on RAM, starting first with the way that Windows manages the RAM for a process, and then we'll move on to the way that, again, like we did last time, the way that it manages RAM for the system at large. Processes have RAM assigned to them called the working set that Windows keeps track of in lists that they call working set lists. The list entries are the pages of RAM that are assigned to a process. And a process always is born with having nothing in its working set. This is part of the demand paged memory management system I introduced, where the process starts up and allocates virtual memory and then starts executing code on the first page of its virtual memory, which causes a page fault, which causes the memory manager to say, I need to give this process a page of RAM, and I need to put in that RAM what that process is trying to access. In the case of Notepad's initial thread executing Notepad's starting code, that page is going to have Notepad executables code. It gets read in from disk into a page in RAM, and then that page is put in this list. And the system knows that Notepad owns that page of memory. There's two types of faults. I just mentioned a page fault, which is what happens when a process touches a piece of its virtual memory that has no corresponding entry in its working set. When that happens, if the system needs to go out to disk to fetch the data or code that the process is trying to reference, that is called a hard fault. If it can find that data or code elsewhere in RAM and just take that page and put it in the working set list, that's called a soft fault. Soft faults are obviously much more efficient than a hard fault. Hard fault, you're spinning up the disk and going and doing disk seeks and reads. And so the thread that incurs the page fault is stuck while that fault is serviced. Other threads in the process can continue to execute. Somebody asked me that at the break. What happens to the other threads in the process? They continue to run. Just the one that faults is stuck waiting for the page fault to get resolved. Each process has a default working set minimum and maximum, and these are numbers that you will see referenced in MSDN. And we're going to take a look at the working set minimums and maximums here in a second in Process Explorer. The working set minimum and maximums actually had a lot more significance in the early days of Windows and NT, and also in the days of VMS. Back when the memory manager used whatever was set as the minimum and the maximum as kind of heuristics for how much working set it should try to have this process run within. Today, minimum controls the maximum number of pages that the process can lock in memory, and it also is used as a reservation for the process, counted against the RAM of the system. In other words, when my working set minimum of me as a process, and I can change it by calling set process working set, if I set that to 512 meg, that means that I've reserved basically that much physical memory for me. And now the system can use that physical memory for other purposes, but if I want it, I get it. And if I've got 1 gig of RAM and I set a process working set min of 512 meg, I can't create a second process with that working set min because the system wouldn't be able to reserve that amount of physical memory for me. Now, most of the time, processes don't use it in the sense of reserving memory for themselves. They use it purely as the setting for the virtual lock, and very few processes do that, but I will show you a few as we go through here that actually do lock memory. The working set maximum is actually completely ignored these days. And the system uses its own heuristics based on the behavior of that process with respect to the behavior of the other processes in the system to decide how much working set a process can have, how big it should grow and how small it should be, completely independent of that minimum and maximum. And if memory gets tight, something called working set trimming kicks in, which is the memory manager going to the list of various processes that it believes it wants to trim from and stealing pages off the working set. Working set, when the memory manager decides the working set's gotten to a large enough size for the process. So the process working set grows and grows and grows. At some point, it wants to touch another page of memory that's not in its working set. The memory manager says, OK, enough is enough. We're going to cap you at this point. And you want another page of memory? Well, I'm going to take one away from you at the same time. And it takes these pages out of the back end of the working set. So it's like the process is eating memory, and the memory manager's pulling, memory out. Now, you're not going to forget that, are you? This is called a local page replacement policy. Instead of having one giant list with all the pages in the system, like many Unix memory managers have, each process has its own list that it'll start eating itself away in a local replacement policy rather than a global one. The pages are put in a least recently used order. And something called page aging is used to figure out where these pages go on the list. Page aging is a process where the memory manager does a mark and sweep algorithm, flushing through physical memory, clearing the access bits on the pages of physical memory. Each page in the hardware has an access bit flag. When something touches that page of memory, the access bit flag gets flipped. And the memory manager comes back through a second time, and if it sees the access bit set, it says, oh, this page was recently accessed. If it wasn't set, then it says this page is old, and it increases the age of this page. And so it keeps track of ages. Now, this accounting, this sweeping, can affect the performance of the system. So the memory manager only starts aging pages when available memory gets low, and I'll talk about how the system knows when available memory gets low in a little bit. There are two types of pages in the working set. There's shareable and there's private. Shareable, just like when we talked about shareable virtual memory, can be shared, but it's not necessarily. Private is, of course, pages that are totally private to the process. And you can imagine those types of working set pages map directly to the types of virtual memory that they correspond to. If I've got notepad.exe page, that's a shareable piece of memory because notepad.exe can be shared with other notepad.exe instances. That would fall into the shareable category. If I have a heap page or a stack page, that's private virtual memory. Any RAM that I'm given that backs that memory in my working set, that's going to be private working set. There's a number of performance counters that you can look at that break down these working set types for a process. There's working set shareable, working set private, working set total size, which is the size of private and shareable. When you're looking at the cost of or impact of a process on the system, one of the things to keep in mind is that processes can have pages stolen away from their working sets and then put in other parts of the system, other pages that are cached, pages essentially, that if the process wanted it back, it would soft fault them in. And those pages mean that the process really used them recently. They're just not owned by it at this point in time. And that really can be considered part of the impact of the process on the system. One of the tricks that some memory-intensive third-party utilities pull to look like they're really not doing anything with your system is when they're busy, they allocate a bunch of memory, their working sets grow very large, and then when they're done, they call flush working set, an API you can call that says empty my working set. So now all those pages get tossed out of the working set, but they're still in RAM. And you go look in a tool like what I'll show you, Process Explorer or Task Manager, and you don't see it show up. It looks like, hey, this thing is just sitting there doing nothing. It doesn't need any RAM to execute when really it has these bursts which causes massive flutter on the system. In Task Manager, as we saw before, the only counter that it shows you by default is this one right here. Okay. I have a feeling that what happened is that this is the a previous instance of Task Manager that ran into problems when memory was low that I haven't exited. And yeah, that's what happened. So it was broken, and now it's fixed. So this is the default column, the memory private working set. This shows you the amount of the working set that is, of course, backing private memory just for the process. And remember, I told you that most cases, the memory leak that we talked about, that can be tracked by looking at private bytes, the virtual private bytes column. That, again, here, this is the obviously direct impact of this process in terms of its physical memory footprint for what the system thinks it needs right now. So this is probably a decent way to look at how memory hungry is this process by looking at this private working set. But it's not the whole picture, of course. Process Explorer, you can add a whole bunch of other columns. Let's go and add a bunch of columns to the main tree view here. If I go to process memory, I can add minimum working set. Let's go ahead and see what the minimum working sets are. Total working set size, as we'll zoom in here, shareable bytes, private bytes, shared bytes. And you can see I have maximum working set and peak working set size. So we can see how big the working set got over time as well. And now zoom out, and let's slide over here. First, the minimum working sets. You can see down here there's one process that set its minimum working set to something that's not the default of 200K, which everybody else has. This one set it to 51 megabytes. So, and I'll explain later why it did that, the min working set. Now, if you take a look at these other columns, working set, peak working set private, working set shared, and working set shareable, you'll notice that I'll point out again that the shareable subset of the shareable can be shared. And in this case, 3.2 meg of that 3.9 meg of shareable is shared with some other process. Some other process on the system is sharing those pages from this working set. It could be DLLs, for example, that are mapped into multiple processes. And if the private can't be shared, these are the same numbers we saw in Task Manager. Now I'm going to run test limit 3 times to show you a third type of test limit, which is one that allocates committed memory and touches it all. And when it touches it all, it's going to look very memory intensive. So here's our -R. This is going to reserve 1 gig of memory. Test limit -M, that commits 1 gig of memory. And then test limit -D says commit it and touch it all. So it's going to touch 1 gig. You saw it took a little bit longer than the other ones. And if I go now and find test limit, shrink this down, slide this over, and let's see if we can tell the difference between these. So here are the 3 test limits. Right, 2, 3. Now, which one is the one that touched all of its memory? Yeah, the first one is, obviously, it committed 1 gig, and then it touched the whole thing, and the system let its working set actually grow to the 1 gig it wanted. Which one's the one that reserved memory, and which one's the one that committed memory? How many people vote for the bottom one is the one that reserved memory? How many people vote for the top one, that middle one, is the one that reserved memory? It's a trick question. You can't tell. Just wanted you to raise your hand. Yeah, the only way we could tell the difference, actually, is if we went and looked at how much they actually committed. Now you can tell the difference. Which one's the one that reserved? The bottom one. So this one reserved, this one committed and touched. And in Task Manager, we would see, if we sorted by memory private working set, which is the only, like I said, is the default column, we would only see one of them, when in fact 2 of them are having an impact on the system commit, and in terms of our ability to actually run programs, not necessarily run them well, but run them, both of them are equally impactful. Now, as far as running them well, this one will have the most impact because it's the one that's actually demanding use of that memory. When we take a look at VMMap, we can get a deeper look inside of a process. So I've got a couple of notepads. Let me start with a fresh notepad. And I've got a VMMap over here. Let me start with notepad. Why do I have two notepads? And we've got now up here a third graph that we're going to look at. This is the working set graph, and this is going to break it down with the same color codings that we saw for the committed and the private bytes graphs. Most of the working set of this notepad is in its images. Then you can see almost all the heap is probably in the working set. Only some of the virtual memory that was committed is in the working set. And then when we scroll down here, we can see the columns that correspond to working set. Here's private data. 21 meg is the sum of the reserved and committed. 4 meg of it is committed. All 4 meg of that is obviously going to be private. And only 560K of that is in the working set. Uh-oh, what's that? There was no shareable over here. Actually, the committed and the private sum to the same size. So what's going on here, this 4K? There's a special page in memory that's shared between user mode processes and kernel, which is a 4K allocation of private memory that actually counts as shared because the kernel and user mode communicate through this page. And that's what that 4K is from. If you look at the images, most of the images, total working set 10.2, only part of that is private. Almost all of what notepads got loaded into memory is shared with something else, almost all of the files. Let's go see which ones it's not shared. From this, if we go down here, I've got the columns moved over here. So if I say how much is shared and how much is shareable and how much is private. So private, or actually what we want to do is find the difference between shareable and shared. And you can see that here, this one DLL, 1.9 meg is shared, only 1.5 is shareable, and that is shell 32. And that means that some other that the notepads exercised parts or touched parts of shell 32, faulted it into its working set that no other process has currently in its working set. One of the ways that you can see the benefits of sharing pages like this across working sets is by running multiple processes of the same application at the same time, which is what you'd be doing on a terminal server system. On a terminal server system, it would really suck if everybody that ran Office had their own private copy of Office loaded into memory. Because of the sharing that you see here in the working sets, now everybody can share most of the Office executables and even a lot of the Office data across their working sets. We can demonstrate that by watching, let's see, notepad.exe, because I've only got one notepad running. Let's find notepad.exe right here. And as you would guess, its total contribution to the working set is 52K, 16K of it's private. That means copy on write pages, which I'll talk about. 36K of it's shareable, but nothing is shared. That's because nobody else has notepad.exe in their working set. If I launch a second notepad now, what do you think that number is going to turn into right there? 36. So it just got moved into the shared column because now that other notepad also has those pages in its working set. Copy on write is something that I've been referencing multiple times. Copy on write, like I mentioned before, makes it possible for processes to start by sharing memory, and then if one of them wants a private version of it, they can get a private version without affecting the other process. What we saw with that 16K of private in notepad.exe were probably global variables that Notepad was setting and causing this to happen right here. Initially, notepad.exe's image file was mapped into both address spaces in both working sets, and there was a page of data there where global variables are defined where Notepad would set things like its window position. X and Y coordinates. And when Notepad goes and modifies that, it gets a copy of that page that only it sees, and it's in its working set now. And that's virtual memory maps to that now private, what's become a private page. This is what's called internally a split page in copy on write terminology. That other instance still sees the original data. If it modified it, it would also get its own copy. And that's why we saw that 16K of private in the notepad.exe address space. So that's a little bit of look at how working sets assigned and split across different parts of a process's address space assigned to it. Now let's take a look at the way that the system manages physical memory as a whole, and then we'll understand how pages flow through the system into and out of processes as various operations occur. There's a number of lists that the system keeps. We've already just talked about the working set lists, which are the lists for each process of the pages that are owned by that process or shared with other processes in some cases. But then there's lists where unassigned physical pages are also kept, the pages that aren't in anybody's working set. And there's the free list, the modified page list, the standby page list, the zero page list, the ROM page list, and the bad page list. These are pages that have been very naughty. They're put over here on the side, and nobody can play with them. Actually, there are pages that were detected with ECC scanning memory checks at system boot. Also, the system does some ECC checks and some memory checks, too, while the system's running. The memory manager, as a Vista, for pages that are on the zero page list, it will go and see if those pages really are zeroed periodically. And if they're not, then it says memory problem and flings them off onto the bad page list so nobody can use them and writes an event to the system event log. Turns out that a lot of OEMs, on PC class systems, they're not ECC memory, and memory problems, memory errors off bit flips do occur pretty frequently, it turns out, looking at telemetry that comes in. And so that's Windows' attempt to protect you from that. These lists are all implemented by entries in what's called a page frame database. The PFN database is called, page frame number. Windows has the database where all of these pages have data structures associated with them. All of RAM is represented by an entry in this database that is also mapped into RAM. And the lists that I'm talking about are actually linked through those pages in the database. So the zero page list is basically a front link pointing at one of the pages, and then that page points at the next one in the list, that page points at the next one, and so that list weaves through the page frame database. Same thing with working sets. Working sets are separate lists, but they point at these pages in the PFN database. And these lists are all as FIFO lists, or queues. These next few pages are text descriptions of what I'm going to describe on this diagram right here. So yes, the slides are going to be available, so you can go back and refer to the descriptions. But I'm going to walk through graphically what's going on here. Fortunately, the template here made it hard to read one of these things. So let me change the colors and then come back. So the system boots up. Let's start with the big bang. Windows boots. You power on the PC. Initially, all RAM is sitting on the free page list. And what happens is this thread called the zero page thread wakes up. Its sole job in life, it's the first initial thread of the system. After that thread initializes things, becomes the zero page thread. And that thread's only job is to zero pages. It's a very simple job, but the zero page thread does it extremely well. And so when it sees pages go onto the free page list, it says, oh, work to do. Its life is fulfilled when it zeroes pages. So it wakes up, and it actually tries to zero them as quickly as it can. It kind of has a race against itself, like how fast can I zero them this time? So it zeroes them, and it puts them on the zero page list. So after the boot, everything is on the zero page list. And now we start to create working sets. Working sets get created initially when the system's booting from the zero page list, because that's the only place where there's pages. So notepad.exe or a kernel driver starts executing. System wants to add a page to its working set, or not a system driver because they don't have working sets, but process, session manager process, one of the first ones. gets its page given to it from the zero page list, and then it starts scribbling on it whatever it wants to. Eventually, its working set gets big enough that the memory manager says, okay, you've gotten a little bit too big, time to go on a diet, and we're going to start stealing pages away. Where it puts those pages depends on what's happened to those pages. If the pages have been modified, then they can't be reused right away. Those pages contain precious data that if we overwrote it with something else would cause the process to not have lose data. It could be Notepad, the data that Notepad stuck in its global variables. If that page gets pulled out, it goes to the modified page list because we can't give it to some other process without first writing it back to disk. And it's actually the job of a modified page writer to take those pages and write them out to disk. So when it's a little bit more lazy than the zero page thread. The zero page thread is just like I want to zero every damn page that gets on that free page list, and I'm going to do it as fast as I possibly can. The modified page writer is like the guy, he's been around the block a few times, he's kind of old, worn out, just kind of tired of things. He's sitting there having a beer, reading the paper, and every now and then he looks over at the modified page list, he sees stuff to start to pile up there, and he'll go, all right, he puts down his paper and start to put those things, move them over to the standby list. And then he'll move some of them, he won't move all of them, and he'll go, that's good enough. And he'll sit down, and he'll go back to drinking his beer and reading his paper. He probably has a white t-shirt on and stains on it. That's what I imagine. And so his job is moving these pages to the standby list after he's written them back to disk. And you could kind of understand why he's a little more lazy, because writing them to disk is a lot more work than just simply zeroing them. So he gets tired out pretty quickly. But the pages then are on the standby list, and also pages that weren't modified when they're pulled from the working set go to the standby list as well. Those pages can be reused right away. We can zap them because the system knows where to go get that data again. That data can go to the paging file or a map file on disk. If it's an executable page, like notepad.exe from an image, it's a shareable page, and it gets pulled from the working set, it go right to the standby list as well. So you can think of the standby list really as reusable, instantly reusable cache. It's cache data, has data that processes had been using at some point in time that they may want to use it again, and we can soft fault that back into the working set. The modified page list also has cache data, but it's not usable right away. We have to kick the modified page writer to get him to move them, write them to disk, and move them over to the standby list. The case that I just showed you of Notepad starting up and one of those, those shareable pages of notepad.exe move into the shared column, that's what's called a global valid fault. That's a page fault that's satisfied from somebody else's working set. So with that second Notepad, when it touched those pages, the system looked and said, oh, those pages are over in this other Notepad's working set. We're going to map them into your working set as well. So now they're in two processes' working set, which is a very important thing to remember, because that means if you go to Task Manager and you add up that private working set column, well, actually the private working set column doesn't account for the whole thing. If you add up the working set size, or you even add up the shareable working set size, you're going to be double counting pages, because a lot of pages are shared between multiple processes. So the next transition is when a process, that's that bottom line there, pages going from the working set list to the free page list. That happens when a process frees virtual memory, frees private virtual memory. Heap, stack, thread exits, stack is freed. Or DLL unloads and it deletes its heap on the way out. Or you call virtual free on a block of memory that you called virtual alloc that was private bytes. Nobody cares about that data anymore because you were the only guy that cared about it, and now you don't care, so let's toss it. No sense in putting it on a modified page list. You're not going to want it again. No sense putting it on the standby list. Nobody wants it. So let's put it over on the free page list. It's got garbage on it now. Because it's got garbage, we can't immediately give it to anybody else either. We've got to zero, well, in most cases. Some cases we can actually give it to somebody else, but in most cases we can't. So that's why the zero page thread is sitting there ready to zap pages and fill them with zeros. Because the zero filled page can be given to anybody without worry about any kind of security issue. If we took a free page and we wanted to give it to somebody, put it in its working set, we would have to make sure it couldn't see what was there before we gave it to it. Because it could be looking at data from another process. It could be another even secure process, or sensitive process might be passwords or some other sensitive data. We've got to make sure that it doesn't have access to that. That's part of Windows C2 security requirement. So that's the purpose of the zero page thread. But there are some allocations that can be satisfied from that free page list. In fact, there's some allocations where you'd want to satisfy them from the free page list. If there's pages on the free page list, and there's a page that the system is going to immediately overwrite with data before the process sees it, then we'd like to just get it from the free page list. We don't need a zero page because the data in that page is going to be zapped before the process sees it. We don't want to waste the work that the zero page thread has done to zero page. Let's just go take one of these free pages. Example, you call read file API. You're reading data from disk into your virtual memory. So what you've done, you've allocated some private data by calling virtual alloc. So now you've got your buffer, and then you call read file and pass that buffer into read file. Read file is going to go do I/O into pages that it is then going to put in your working set. That I/O can go into pages that are pulled from the free page list as long as that I/O completes before those pages are put in your working set. So you can't see them. So you can't see them until they're in your working set connected to your virtual memory. So what happens is the cache manager, the component in the kernel that does those I/Os, the I/O system with the help of the cache manager, will go and allocate pages from the free page list if there's pages there to allocate from, read into those, and then put them in your working set. No sense taking a zero page. But if you do a virtual alloc always comes scrubbed, always filled with zeros. When you look at it, it's clean. You don't see anybody else's stuff. And so if we want one of those, it's got to come from the zero page thread, from the zero page list. So that's why these allocations can happen from both of these pages, depending on the purpose of the ultimate page, whether it's going to be referenced as zeros or whether it's going to be immediately overwritten with data from disk. And then finally, soft faults. Soft faults happen, like I said, when pages were taken out of a working set. Now the process touches that page again. So Notepad.exe touches one of its pages in its code at startup, system startup, and doesn't touch it for a really long time. And eventually, through paging dynamics, that page works its way back to the tail of its working set, gets pulled out, put over on the standby list. But then, at some later point, Notepad goes and tries to execute that code again. Soft fault. System says, hey, I've got that page in the standby list. I can just put it back in the working set. So just highlighting the fact that that's a cache. And same thing with modified page. Page can come right from the modified list without ever getting written to disk and go back in a working set. So there's a few ways that you can look at the sizes of these paging lists, or at least some of the paging lists. Now this is some of the confusion with Task Manager that I think is kind of interesting. Shows you kind of the thought level of the Task Manager guys. So at the top, we've got Task Manager from Windows XP Server 2003. And we've got this section over here called physical memory. There's two values there that I'm going to be talking about. Well, total, the amount of RAM you've got. Available and system cache. What is available? Available is the amount of RAM that's on one of those lists that can be reused without a disk I/O. Let's see if we can figure out what would correspond to available. Would the zero page list, pages on that list, be counted and available? Yep. How about pages on the free page list? How about pages on the bad page list? No, good, just checking. How about pages on the standby list? How about pages on the modified page list? Do I have to do an I/O before I can reuse them? Yeah. So I've got to do a disk I/O, so these aren't going to be available. What about working set pages? No. So what is available? The sum of what 3 pages or lists? This one, and this one. So going back to here, that's what we've got on those 3 lists, sum up to available. System cache. System cache is the sum of the standby list plus the sum of the modified page list plus one of the working sets. The system working set, it counts as cache for some reason. And that is what shows up in that system cache value over here. So that's some of those lists too. The standby list is in both of those, counted in both of those. Now, the thing about this task manager view is that customers, people using their PCs, would use them and they'd look at this, they'd open up Task Manager, and they'd come to this page, and they'd see available was always high. And they'd say, Windows isn't using my RAM. Shouldn't it be doing something useful with my RAM? It's just sitting there doing nothing. It's available. And so they call Microsoft customer support and say, why isn't Windows XP using all my RAM? And the guy on the tech support, would say, well, your system actually doesn't need that to use that RAM. It's actually good that it's got available memory. But so many support calls came in that the task manager guy decided, hey, all right, I'll help out the PSS guys, and I'll get rid of the available thing. Yeah, so now there's free, which you know what free is. It's just the amount of memory that's on the free page list. Well, what does the 0 page thread do with that? Frees it, zeros it. Well, it's actually the sum of both of those, free and 0. But free on Vista, well, on XP, if they put free would actually have some data on it quite a bit of the time, because available standby plus modified, available standby plus 0 plus free. But the problem is on Vista, when they added this, Superfetch was also introduced. And what Superfetch does is goes, oh, there's free memory? Well, that's a waste. I should be putting stuff in that you might need. So it goes and does disk I/Os, fetching data into RAM, and then those pages go to the standby list. So the free amount of memory you've got free on Vista or higher on client is almost always nothing, because Superfetch is so good about making use of it. So now what happens is customers started calling in and saying, what are you doing with my memory? You're wasting my Windows, and this was bad timing, you have to agree, because this happened in Vista. And so everybody's like, oh, no wonder. Free, there's no free memory. Windows is such a pig. And, it might have been, but this number didn't help. So then the task manager guys said, all right, now we've got to deal with those support calls. What should I do? So now everybody's confused. What? How can there be memory available, but it's none free? I don't. So the support calls are now double what they were before. Cached is still what it was before, by the way. Just they removed the word system from it for some reason. So that's the tale of task managers reporting of these numbers. How about Process Explorer? I tried to be a little bit more sane here. So let's pull up Process Explorer. In Process Explorer, I actually break it down by list. So 0, free, modified, no write, which is a list that I didn't mention because it's a special purpose list used by NTFS. So NTFS has transactional semantics writing data to disk, and it doesn't want the modified page writer to write these things back before it wants them written back. So it puts them on a list that's a special list that it has full control over. And then here's the standby list. And then you can see the standby list is broken down into sub-priorities, which I'll talk about in a little bit. But you can see that, as I mentioned, that the free stuff just goes right to zeroed. And whenever something shows up on free, that 0 page thread is just right there to pick it up. In fact, we can do a cool little trick to see the 0 page thread at work. And the way that I'll do that is by Where's that? Mouse is acting funny. Where's that, that one where that dash D one? Here's this one. So when I terminate this, those pages are private pages. They're modified because not my test limit modifies them. So that these are going to go instantly to the free list. And then the zero-page thread is just going to wake up and cry with joy, dump them all to the zero-page thread. So sometimes we can see the free page list show up with a whole bunch of pages, and then you'll see the zero-page thread list grow to that same size. Okay, here we go. Keep your eye. Actually, I can zoom in. Okay, keep your eye on the free and zero values there. Oh, we didn't catch it. It was so fast. It's good. That's good. It's getting better. But trust me, that's what happened. They went to the free page list. I mentioned that, that looking at the working sets doesn't really account for the full view of the physical memory that's in RAM that is really associated with a particular process. When pages get stolen from the working set, if they're private pages, the system keeps track of the fact that those pages are connected with this process. And I'm going to launch a process tool called RAMMap now that will show you the pages that are associated with the process, and I'll come back to this tab in a second, that are associated with the process and yet not in its working set, that might be on the standby list or the modified page list. Let me show an example here. And what we can do is take a test limit, and I'll do a test limit dash D of, let's do 2048 C1. So this is going to touch, oh crap, paging file problems, 1024. And then let me use RAMMap. And what I'm going to do with RAMMap is use a tool command here. Oh, I have two test limits. Let me exit this one. And I'm going to use a command here. You can see it's working set, boom, full of 1 gig. But I'm going to do empty working set. Now working set's almost nothing. What that command does, it says shrink working set down to nothing, as close to nothing. And now already you can see it's test limit just in the act of living touches 3 meg of code and data. Well, actually, and part of its living is 512 down here, or page tables of 3 meg. So that's that 3 meg just to live is page tables mapping that entire 1 gig. Now, where did those pages go? Let's go back and take a look at RAMMap, do an F5 here, find test limit, and you can see that test limit has a total of 221 meg of that 1 gig that it touched is still in RAM. Most of that is on the modified page list. Through 219. What's happening now is the modified page writer is still writing stuff to disk. And in this case, because we did you can see some of it moving to the standby list here. To another F5. There's another 7 meg. So as it's writing, it's moving to the standby list. And it's probably, at this point, also repurposing that standby pages for other things, which is why we didn't see it with its full 7, it didn't add up to 1 gig like you would expect, because it already reused some of those standby pages for something that it thought was more important. Superfetch probably stole them. That damn Superfetch. So you can see this continue to grow as the modified page writer lazily, taking its own sweet time with beer in the middle, is writing stuff back. Let's go back to that main page of RAMMap. And this is one of those things where when I wrote this tool, it was like, ah, because this gives a view of physical memory usage in Windows that no other tool has ever shown. And just writing a tool where you can look and have like this X-ray view of what's going on was just it's a very cool feeling. This top bar across here is looking at the pages, the lists. So you can see when I hover, I'm over this gray thing, steel gray, a standby list. This is the active page list. Active means it's in a working set. And this green is modified page list. This gray is in the zeroed page list. And over here, there's some free pages. Or zero pages over here, zeroed. It's a lot easier to look at a graph and see a breakdown. You get a feel for how memory is being used at this point. So about half of RAM is being used by processes. The other half is mostly cache, standby, and modified page list. And then the zero page thread, about a quarter of it applies to that. Those correspond to these columns right here. And these columns, you can see, add up the totals to these values up here. Then down this left side, we've got breakdown by type of memory. Not what list it's on, but what type of memory, regardless of what list it happens to be on. Starting with the yellow, which is process private pages. Process private pages can live in, like we've seen, either in working sets, in the standby list, or the modified page list. Of the total of 1.1 gig of private pages, so some amount of this active is in private pages, 779 meg. Some amount of the standby list is made up of the process private pages, 172 meg, and then finally 189 meg is of process private pages are on the modified page list. And so that's the way you read through here. But there's some values here that are familiar to you from looking at VMMap, like map files, shared memory, which is backed by the paging file in RAM, page tables, paged pool, non-paged pool. These are kernel buffers. One of them is always in RAM, so it always show up as active. 261 meg of kernel buffers that are non-paged. They're non-paged because the system needs to touch them and make sure it never incurs a page fault when it does so. This is the kind of memory that it will access when kernel locks are being held, and where the system can't take a page fault while certain kinds of kernel locks are held. Then paged pool are buffers that are allocated by the kernel and drivers that can be paged out to memory. System PTEs, these describe mappings for drivers. Session private is terminal server session space, memory, metafile. This is NTFS metadata structures. AWE, I'll talk about later. Driver locked, I'll talk about later. Kernel stacks. These are the stacks that every thread has a user mode stack and a kernel mode stack. The kernel mode stack is by default 24K on x86, and so and 48K or 12K on x86, 24K on x64. So these, you divide by those, and you'll see approximately the number of kernel threads that are alive right now and in memory. And then unused, this is obviously going to be on the 0 or free page list as that remainder. So that's the grid to take a look at how these things cross with one another. If you want to see how much of where's the breakdown of active, you would come and look at that column that active is in and see what kind of data is in that active list. So all of the process data corresponds, that's in working sets, is broken down across these lists or these types of memory right here. Prioritized standby lists, these was introduced with Superfetch. And Superfetch, you saw when I opened up Process Explorer, it looked at the standby list that we saw priorities. By default, every process has a priority of 5. And any pages that get taken from away from a process and put on the standby list get taken and put on the list according to the process's memory priority, which I'll show you in a second. But Superfetch makes use of the other priorities by pre-populating. Like I said, if it sees free memory, it will try to fill it with data from disk. And the way that it learns is based on the history of the system. And it tries to improve things like you resuming from hibernate, performance after something comes and slams memory, frees it, blows it out. It'll try, if it releases it, just like I did with test limit. One of the reasons that we saw no private pages of test limit when I emptied its working set is because the memory manager, or Superfetch, saw all this free memory show up in the standby list, saw it low priority, and it had kicked out higher priority pages, so it started to repurpose those and put in higher priority stuff. Fast user switching, and by the way, this is disabled if you've got an SSD on Win 7 that hits a 6.5 or higher on the win performance test that you get on the computer properties, then superfetch turns off because superfetch's goal is to hide disk seeks. And if you've got a fast SSD, you're not going to see any latency caused by seeks. It's also off, of course, on server. And this talks about the memory priorities. And when we add the memory priority column, here, memory priority, let's see what kind of memory priorities we got. Almost everything here is 5. In fact, that's all I see are 5s. Oh, there's a 1. What is that 1? That is branch cache. So branch cache is that Windows Server 2008 R2 Windows 7 feature that caches data, like a peer-to-peer caching on branch offices. So it's set its memory priority to 1 because when pages get taken away, it says, you know, those cache pages, you're probably more important, so you can have them right away. And the system will eat pages off the standby list starting at the lowest priority. There's another way we can create process with a priority of 1, or 3 actually, a background priority. So I'm going to echo hello to a file on the desktop. And that is going to, did I do that right? Nope. That is going to cause another process to show up right here. And that will be a search in process. Where are you? Search process. Here, process priority 1, and it's the search protocol host that saw that file got created and then went to index it, and it says my pages aren't that important either, so just steal them away. How much of the standby list has been consumed? Now we're getting more close to the question, answering the question, or getting enough data to answer the question, do I need more RAM? By the way, the answer is yes. Just can't have too much RAM. If I go to the priority summary, there's this repurposed column, which will show you, I mentioned that pages get sucked off from the lowest priority page list first. So when a process is memory hungry and it empties these, it'll start eating into higher and higher priority pages. So if you see a lot of pages repurposed off of these lists, then you know that your system was under some intense memory pressure, really intense, to get up and to start eating away at this small amounts of pages here. You can tell that my system was under quite a bit of memory pressure because so much has been consumed off the standby list. Now this is memory pressure at some point since the system booted. We can't really say. And if I ran test limit -d again and had it consume large chunks of memory, we'd see a lot more. We'd see these numbers go up. Let's see if we can have that happen. Test limit -d 1024-c1. And then let's do a refresh and let's see if these numbers change. Well, these got zapped to 0. So it ate those. And these numbers went up by the corresponding amount. So we 8 pages off a lot of these. Now, we might have had pages on the 0-page list that didn't have to get repurposed first, right? Because we're going to eat off the free page list. If that's empty, then we go to the 0-page list. If that's empty, then we go to standby list and start eating into that. So that's cache replacement, working set list replacement is going to go to available pages in those order. We want to eat the least useful pages first, going to be free pages. Second least useful are the 0 pages, and third most least useful are standby pages. If the standby list gets empty, then what do? We kick that lazy modified page list writer. We wake him up and we say, get some pages over on the standby list. So he wakes up, writes pages out to disk, puts them on the standby list. We eat all those. Now, when the modified page list gets empty, then what do? That point, actually, at that point, if memory manager decides that this process that wants memory is more important than other processes, it's going to start eating from other processes. So at that point, it's like, I've exhausted all means available to not do harm, but now I'm going to potentially do harm to existing processes by stealing pages off their working sets. And so that's when trimming will really start to happen. What data is in the standby list? I just have to show this because this is so cool. Let's briefly talk about these other tabs here. This tab is basically a dump of the page frame database. Physical addresses, what is at that physical address is being used for, and if it's a mapped file, where it's mapped, what file it's from. If it's a process private page and it's mapped into a process, with the virtual address of that process. So here's this page right here is in process monitor's working set, and it's mapped at this address in process monitor. This next one is physical memory. So this shows you the physical memory layout by addresses. You'll see gaps in this for devices. Devices that have addressable RAM on them will create gaps in here. So video cards are one example that will create gaps in there. File summary. This is the list of all the pages that are in the standby list or modified page list on the system. So all the data that's cached, the amount that's on the standby list of that data. So let's see what the biggest cached file is. I ran Outlook earlier and I exited it, but most of my Outlook cache is still in RAM. A lot of it is, 32 meg. How about modified? Some IE index.dat file hasn't been written back to disk by the modified page writer yet. Now this is really, before you actually go look at this and somebody else is looking over your shoulder, make sure you have not visited any, let's say, maybe websites with farm animals on them or anything like that. And this is where this really cool demo comes into play. Watch. This is secret data. And I'm going to save that to the desktop. Secret. So it doesn't matter where I save it, but secret.txt. All right, now I'm going to exit Notepad. I'll do a refresh. And let's see if that file's in RAM. And there it is. It's still in RAM. It's 4K. It's all in the standby list. And here's the cool part. That was really pretty cool, wasn't it? But here's the really cool part. If I go to File Details, here's where it is in RAM. All right, you're saying, OK, that's kind of cool, but so what? Well, let me show you. So I'm going to run livekd, which is my kernel debugging tool. Livekd, and point at the local cache, symbols, publics. And there's a command that you can use to dump whatever's at a physical address, 101CAD123. Now, what's that useful for? Impress your friends, I guess. All right, so do you have enough RAM? The answer is no, of course. Depends on who's asking, right? If it's your child, yes, you've got plenty of RAM. If it's your employee, yes, they have plenty of RAM. If you're asking your boss, no, you definitely don't. If your boss asks you, no, I don't have enough RAM. There's no surefire way to be able to tell if you have enough RAM in your system. There's just no number that you can say, look, that number right there says I don't have enough RAM, and it says how much I need. It'd be nice if things were that easy, but they're not. How do you know how much RAM, if you've got enough RAM? Oh, you'll know. That's generally the case. It's just you know. Yeah, I need more RAM. Well, there's some rules of thumb that we follow that Dave and I have come up with over time, over the many years. One of them, the most reliable, is just to watch available memory. Watch that available memory count, and you can add available bytes in perfmon as a counter if you want to log this over time. Or you can watch and process monitor interactively or task manager. If that number is low and consistently stays low, then you likely could use more RAM. Another one, the real sign of RAM is if you're doing a lot of reads from the paging file. That's another way that you can tell if you need more RAM is lots of reads from the paging file. Now, why not reads from files on disk? And why not writes to the paging file? Why don't those necessarily mean I need more RAM? Well, first, reading from files on disk could mean you need more RAM, especially if you've got an app that is just hungry, sucking through data on disk, and it's sucking over the same data over and over again, and it has to keep on going back and reading the data from the same files because it can't fit all the data set in memory. Then you could use more RAM. But it's really hard to detect that pattern. And I separate that pattern from just general, I'm doing disk I/O. If I do a giant file copy operation, if I copy a multi-gigabyte VHD from one place to another, I'm going to see a heck of a lot of disk I/Os coming from a file. Page faults even, because copy does memory map file I/O. And does that mean I could use more RAM if I'm not going to access that VHD again? No. Basically, RAM at that point is just a tunnel that the data is flowing through. I could add more RAM. The tunnel's not going to, the size of the tunnel doesn't matter. I could have all that data basically funneling through the largest disk I/Os I can do kind of size of pages, and that's the max that I'm going to help the copy operation. Other than that, throwing more RAM at the problem is not going to help. But and what about writing to the paging file? Does that matter? If I'm writing to the paging file, that could mean I could use more RAM because that means data or code data is being pushed out to the paging file that was in RAM. And if it's being pushed out very quickly, that could mean that some memory-hungry process is coming and ballooning things and shoving everything out. Actually, this brings me back to one of my pet peeves back in the late 90s and early 2000s were these RAM optimizers. Anybody ever buy a RAM optimizer? So RAM optimizers, I actually wrote one myself. I made quite a good bit of money off it, too, but I wasn't proud of it. No, I'm just kidding. I didn't sell it. Talks, tools. So what RAM optimizers did back then is they said, we want to RAM optimize you. And how did people determine how much RAM they had available? Or is they'd go and say, what's my available bytes? Where's available? Actually, I don't even show it here. They'd go at Task Manager. And they'd say available, 1.9 meg, or whatever. It's low. Actually, why don't I go ahead and get rid of available? Test limit -D 1500. Now I'm leaking, and my available number, woo, it went way down. So they would say, oh, optimize. Do you want to optimize manually or every now and then? I would say, well, let me optimize right now because my available memory is a little low. Optimizing. And this is doing such a great job of optimizing, it takes a while. I'm just going to exit it, and you'll see its effect. Oh, wow, look at that. I just increased the amount of available. This worked better pre-Vista, by the way. But what those RAM optimizers do is just do what test limit does. They allocate a ton of RAM, a ton of virtual memory, touch it all, and then free it. Where does that go? What list does all those pages go to? Which page? Which list? Which list? Free? How many people vote on free? How about 0? Eventually, yeah. Very quickly, they'll go to the 0. But they go first to the free, and that is part of what makes up available. And so available will shoot up, and they go, wow, that is just awesome. It's like there's these memory leaks in Windows that is just releasing. It's forcing Windows to release memory. It's the coolest thing ever. And what happens, though, is that you start to use your system again, and now all those pages were just sent out to the paging file or tossed, and they have to be fetched back in from disk. So that's the snake oil that was RAM optimizers. Like I said, I never sold that one. One of the ways that you can watch for reads from the paging file, which is what happens then, because we've just simulated a memory-hungry process where we could actually have better performance if I had more RAM, because that thing is very memory-hungry and it's forcing everything else out. If I had more RAM, we could keep more in memory and have better performance. But we can't necessarily see from the writes, because that could be a one-time thing. We can see, if we start to read those pages back in, that, yes, those pages that were sent out are actually useful pages the system needs. They were thrown out, and now we've got all this paging back in, so that at some point in time, we could have used more RAM. And the way that you can see paging reads is by using Process Monitor. And this slide will show you how to configure the filter so you can watch paging reads. Now, one of the problems is if you're under memory pressure, even running tools like this is going to be painful. But this is the formula to do it. Let's conclude now with some hard-to-track memory, just to show you that there's these dark corners to be aware of. Reserve memory seems like one of those things that should be free. I should just be able to reserve memory as much as I want, and no big deal, because I'm not committing the memory. I'm not doing anything with it. Big deal. It turns out that reserved memory has a charge with it. Part of it is that page tables are reserved. The system says, yes, you reserve this amount of memory. If I had to create page tables, if you wanted to commit that, and I had to create page table entries for it, this is the amount of page table pages that I would have to create, and I'm going to charge that against the system commit limit. So the more RAM you reserve, the more page tables that would be required to describe that virtual memory if you actually committed it, and so that gets charged. And you can see here, test limit allocating 1 gig 10 times. So 10 gigabytes, reserving 10 gigabytes, or whatever that is. 1 is 1 megabyte. So 10 megabytes, 100 megabytes, 1 gigabyte. Oh, it's 100 gigabytes times 3. And you can see that this test limit ballooned to 1, that's a big number, 1 terabyte. And the private bytes usage is pretty big there, 1.8 gig. Here's test limit dash 64. On a 64-bit test limit, look at it consumed its whole address space. I made the paging file big enough to do this. 8 terabytes, virtual size, private bytes, 16 gig, just by reserving memory. So that's a hidden cost. And then it also costs to describe the virtual address space that's just that reserved memory. So this is poolmon, which shows you page pool and non-page pool allocations using that same test limit 64 test. You can see that I've sorted by pool tag. And remember, these are kernel buffers. These are allocated by the memory manager. The buffers are tagged with names. The memory manager tags the ones that describe address spaces with this VAD-S. And there's been a ton of allocations, and the amount that's currently allocated is this amount right here, which is 640 meg. So not only that system commit, but also page pool, non-page pool rather, which is a very precious resource, because non-page pool, once it's allocated, it's basically created this hold inside a RAM, this like block nobody else can mess with. Shared memory, this is a hole that I think is one of the most devious, insidious ones. And this one's really easy to exercise. Fortunately, just fortunately, there's not that many cases that I've come across where this has been the problem. But when it is, it's just incredibly hard to track down. Let me show you a demo of a shared memory leak. Shared memory, remember, if we allocate shared memory, it doesn't show up in private bytes because it's not private. It's shareable. Even though it's potentially not shared, and it really is effectively private, it's not going to show up. Further, what Windows does, when you create a shared memory section, you create a section, you specify how big that section is, and then you map parts of that section into your address space. The way we saw earlier in part 1, the way it showed file mappings, works the same way. You create this virtual file mapping of this shared memory, and you map parts of it into your address space. You don't have to map the whole thing. When you create that shared memory, that's when the system commit is charged for that whole block of shared memory. But you will only see it in the process address space if that process maps it in. So the process could create a 1 gigabyte shared memory section. That's going to cost the system commit 1 gig to back it. And if it maps 4K, one page of it, that's all you'll see in the process address space is 4K of shared memory. You won't see that fact that it's backed by this 1 gig giant block. And I'll demonstrate that for you right now. Test limit -S to leak shared memory. I'm going to do 3 gig of shared memory. Paging file is expanding. Let's go take a look at what we can see from test limit. So virtually, test limit looks like this. Virtual size, 41 meg. Private bytes, 1 meg. We could look at any counter in the system, from that to the working set lists counters, and we cannot detect the fact that this process is the one responsible for that giant bump right there. And that is the deviousness of a shared memory leak. Now, there is a way to figure out what it is, but you've got to know what you're looking for, and you've got to know how to use a kernel debugger. So that's one of the big ones. The next one is one that is more commonly run into. This one's also interesting. Remember I showed you virtual locked pages? And we saw in process monitor, wait, where did we see the virtual locked pages? Oh, I remember. We saw the minimum working set for one of these processes was not the default of 200K. In fact, there's 2 of them. And one of them is, you can see DWM over here. Anybody know what DWM is? Yeah, the desktop window manager. This was introduced in Windows Vista. It does the Aero Glass compositing stuff. And to be high performance, it locks data in RAM. That's why its minimum working set, it's set to above the default so that it can lock RAM more than 200K, because remember, the working set minimum dictates how much you can lock. Let's go take a look at VMMap, DWM. Here, and we can see locked here. There's shareable memory, 10 meg, it's got locked. And that locked memory is locked because it's storing graphics data, and actually you can see there's a whole bunch of chunks of it here in the locked column. Locking little bits of graphics, little bits of Windows images. The thing is with locked memory, it's kind of an interesting thing because when you lock memory, you're overriding the memory manager. You're basically taking a chunk of RAM and you're saying, this is mine. Nobody else can do anything with it. This can affect the system's ability to hibernate, for example, because the system needs a certain amount of contiguous RAM to be able to generate a hibernation image. If somebody's locking a large amounts of RAM this way, they can prevent the system from hibernating. It also prevents contiguous physical memory allocation, which can affect device drivers that need to allocate contiguous RAM. This is, in my opinion, a hole that was created for the sake of performance in Windows Vista because, well, actually, there's many holes in Windows Vista, but actually, there's many ways to denial of service attack Windows. This is just one of them. On a Windows Vista system, even somebody without any advanced privilege can lock memory because everybody needs to be able to run Aero Glass. It's not like if you log in with standard user rights, you can't run Aero Glass. So the permission that used to be an admin permission to be able to lock RAM, now everybody's got it as of Windows Vista. And so this can allow a standard user to be able to kill the system by locking RAM. And you can run test limit -L, and I'm not going to do it, but test limit -L 1000, let's lock 500. And I've just locked 500 meg of data. And we see this bump up here, 500 meg. And we're going to see the corresponding effect from those locked pages. Finally, another type of locked memory. And this one's very hard to track down as well. But this one's one that a lot of you probably come across because you've got virtualized servers. And this is driver locked pages. These are pages locked by a driver. And there's 2 drivers that use this mechanism to allocate contiguous RAM that they have full control over. One of them is Hyper-V, and the other one's VMware. If we go take a look at, see my terminal server session still here. This is where I've got Hyper-V running. If I run RAMMap on this system, I've got one VM running, and we're going to try to figure out how big that VM is by using RAMMap. Here's driver locked. How big do you think that VM is? 2 gig, right. That's Hyper-V. This driver-locked memory doesn't show up anywhere else. This is the only place you'll see it is in RAMMap. You will see its effect, of course, on system commit because this counts towards system commit. So system commit, let's just watch that. If I look at system commit here, now it's 4.7 gig when I shut down this VM. Then I just dropped from 4.7 to 2.6. And if I go back, this driver lock memory is gone. Actually, there's still some used by other device drivers, but that's the bulk. So that's, and then there's finally AWE memory, address windowing extensions memory. If you've got x86 and you're running SQL Server in AWE mode, you're giving it, even on 64-bit Windows, it will use basically, SQL Server is one of those apps that just says the operating system's getting in its way. Just let me do it. I know better. And you're just ruining my life by even living. And so it uses AWE memory to carve out chunks for itself and keeps the memory manager away from it. So that's, you will also see that in RAMMap. And it has the same characteristics from looking at the system's memory behavior as we saw for driver locked. Impact system commit, can't pin it down on any process. There's no connection between that kind of memory and the process that allocated it. So that brings me to the conclusion of part 2. So let's just review some of the things that we covered. In part 1, we took a look at process address space usage. We learned the concepts of what committed memory, reserved memory, and process committed memory. Process reserved memory. Then we took a look at private process memory, shareable process memory, which could be shared, and free process memory. We use VMMap to take a look into that. Then we switched over to talk about system commit and the types of memory allocations that count towards system commit, which are all private memory allocations. Could be copy on write memory, could be private bytes, could be shared memory, counts towards, well, actually shared memory counts towards system commit as well. We saw that system commit limit is RAM plus the size of the paging files. We saw how to go change the sizes. We also got educated on how big should the paging file be, what happens when we run without a paging file. And then in this part 2, we took a look at physical memory. What is a working set? How does the system populate the working set? When we took a look at VMMap, how is the working set of a process broken down across the things in it? How are pages shared across working sets when multiple processes are accessing the same data or code? And then we took a look at physical memory paging dynamics. What are the lists that memory is put on? We talked about available memory, which is made up of what lists? There's 3 lists. Free, zeroed, standby, right. And what's the other list? Modified, right. So we talked about those lists, and then finally we talked about how do you know if you don't have enough RAM, with a couple of heuristics. Available is really low. Page reads from the paging file, high, are 2 of the key heuristics. And then we took a look at hard to discover memory, driver lock pages, shared memory pages, could leak. And that brings us to where we are. Everything that I've described is presented, though not organized in the same way. I think that if we have time, we'll reorganize the Memory Manager chapter to follow more the flow that this presentation follows. But everything we've described is in the Windows Internals book. In the Memory Manager chapter, MSDN documents APIs if you're a developer, how to access things like large pages, how to increase your working set minimum, how to lock pages. The best way from a troubleshooting perspective and understanding the way the system uses memory is to do experiments. So I recommend if you're interested in really understanding what's going on, to go back and play with test limit. Test limit has a bunch of different ways that you can stress the system, like I said, from system memory, commit memory, reserve. Try running multiple test limits at the same time and see how the system doles out physical memory to each one. Take a look at the processes you've got on your system with VMMap and see how their address spaces break down. Where are they costing the system physical memory? How are they costing the system commit memory? And finally, come to my next 2 sessions. I've got one tomorrow at 10:15 where I'll talk about Windows Azure and the way that Windows Azure is a distributed operating system, so it's one level up from what we're talking about, although, like I said, everything that I described here still matters in that world. It matters both from us writing Windows Azure because it's running on Windows on the host, and it matters from you writing your apps that run on Windows Azure because you're running in VMs still. So all of these concepts apply. And then finally, I think one of my favorite fun sessions is Case the Unexplained, where I take you through real-world troubleshooting examples with sysinternals tools. And how many people know that I've written a novel? How many people don't know that I've written a novel? Well, actually, you know now, so you shouldn't be raising your hand. Tricked you. So this novel that I wrote is called 0 Day. And it's, if you're in this session, I know you'll like 0 Day. At least there's a really, really high probability you will, because it's, actually, let me show you the video. Since we're over time, you're free to leave, but let me show you the trailer. And try to play it out through the mic here.
Terror is only a keystroke away. Anyone can be the target. The countdown has begun. 0 Day. A new techno thriller by Mark Russinovich.
All right. It's a little cheesy, but it catches your attention, I guess. Anyway, I'm doing a book signing tomorrow at the Tech Ed bookstore at 12:30 if you want to come by and say hi and check out the book. So with that, I hope to see you tomorrow. Hope you enjoyed this and learned something. Thanks.